Swayam Prabha. Digital India. Educated India.
So today we are going to start on a new topic, which is the deflection of beams. Now this topic is extremely visual. You can see it all around you in some of the regular activities that you do, but of course in this course we are going to talk about the concepts of deflections of structural members, and most commonly the structural members, which are beams, right? Now, as I said, that you can see that these concepts being applied to a regular day-to-day life. For example, if you take any particular object in your hand, right, and if you try to say bend it, this bending that you see, it's also a deflection of a beam. For that example, many of you are probably fans of Olympic games. So what you see over here on the figure, that a pole vaulter which is there, and you see that this is, if you consider this this pole as a beam, you can see this beam, because of the weight of the pole vaulter, it deflects. So it's a very visual kind of an aspect that we are going to visit in this particular topic of our discussion, right? Now, in addition to these ones particular to structural engineering problems, you can see n number of examples where the deflections of beams becomes an important aspect. For example, you see this particular warehouse over here, you see how much the beams have sagged over here. Now, deflection of beams, it also plays a role in your feeling of safety. Suppose you are in a room and the beams, you see it has deflected a lot. Although it may be structurally stable, although the structure may be still be able to sustain the loads that are coming on top of the beam, it gives you some sense of unsafety when you're inside the room. And later in your later courses, when you are taking concrete design and steel design, you will see that there are some limit states of serviceability which sort of put some restrictions on how much maximum deflections you can allow in beams. Although the structure is safe, but you have some perception to which you should limit the deflection of the beams, right? Now, deflections of the beams are extremely important for bridges as well, because when the vehicle is moving, you always want to have a feeling that you are moving on a flat surface that is there. So deflections of beams plays a very important role in buildings as well as in the bridge structures. Now, let's go ahead and see that. So what we're trying to do in this chapter is essentially to find that based on the loads that are given on the beams, right, or the structural elements, what is the level of deflection that you can expect, right? And we will rely on some of the things that we have already learned in structural and in solid mechanics until now. So with that, let me just start to poke your memory, or bring back some of the things that we have already studied in this particular topic, and see that how it relates, how from the concepts you have already learned, how can you find the deflection of the beams, or how do we get a sense of the deflection of the beams. Now, from your chapter on pure bending, you must already remember this particular page that is there. So if you see here, when we say it's a positive curvature, that is your beam smiles, you have a sagging kind of a moment. So positive moment corresponds to a positive curvature, negative moment corresponds to a negative curvature. And you see, for the case of pure bending, now remember, in the case of pure bending, let me turn my pen on. Oops, sorry. In the case of pure bending, we know that the moments in both the sides were the same. So you have the same moment overall, and for that we had derived a formula for the curvature, which came out as something like this. Now remember, this equation is a precursor of the equation where you derive the bending stresses. And remember that we had written another equation, that sigma equals to negative of the modulus of elasticity times the curvature kappa times the y over here. Now, and we had used these relationships together to derive that equation, that sigma equals to minus my by I. So these are all kind of correlated over here. But anyway, for our discussion here, let's focus on this guy. So we know that our curvature, that is kappa, is inverse to the radius of curvature, that is the rho, and relates to this particular relationship that is there, is m divided by ei, where ei was the flexural rigidity. Now, in this one, you see it is the kappa was independent of the x. X means along the longitudinal axis of the beam. If you take the x over here, it was independent of that, simply because here the moment was constant. So in the case of pure bending, when we are looking at, the moment is constant, so it is simply a function of m divided by the flexural rigidity that you have over here, right? So this is what we had looked at. But in the general case of loading, as you know, that the bending moment m, it varies from one section to another. We have seen this already when you have drawn your bending moment diagrams. You have seen how the moment varies based on the load that is given. So ideally, your kappa that you have over here, curvature, should be proportional to the moment about the x-axis. So about the variation of the moment, your kappa, so this kappa is also a function of x that you have over here. For example, the most simple example which we can look at is, say, this cantilever beam that you see over here. Now if you see this cantilever beam with a point load at the very tip, at the end of the beam that you have over here. Now from here we know that if you think about from the perspective of the bending moment diagrams and all, this is a free end. So here at x equals to 0 over here, you have the moment as 0, and at x equals to L, you have minus p times L. Why minus p? Because the beam sags like this. So it is a sagging moment, so you have a negative sign over here. Now anyway, the fact of the matter is, here you have a 0 bending moment, so that should automatically tell you that here, since this is related to the moment about here your curvature must be equals to 0, and your radius of curvature, which is inverse of the curvature, it must be infinite, right? As opposed to that, if you come over here at this place, because of the maximum bending moment in the beam, you will have a maximum curvature over here, and correspondingly you will have a value of your radius of curvature rho that is there. So something like this over here. So at this particular place, your kappa is essentially 0. So let's just write that down. So your kappa equals to 0 and your rho is infinite. And in this here, you have a finite value of kappa, which is, minus PL divided by EI. And correspondingly, you have a finite value of your radius of curvature rho v that is there. Okay. So overall, you understand that kappa is also something which varies along the length of the beam as your moment keeps on changing. Now let's take a look at one more example, right? Now let's take a look at this example. This is a more general beam where you have, in addition, in contrast to the one previously where you had just one point load, you had 2 point loads over here. Now how do we now say that how the curvature, so curvature in some sense helps you establish the overall shape of the beam that is there, and we will see how. Now how do we expect the curvature to change? Now we know, since curvature is related to the moment over here, first I have to draw the bending moment diagram. Now before that, I have to go and find out the reactions over here. This is already done in this case, so the reactions which you get are something like this over here. Now once you have the reactions for the beam, this is the free body diagram, you can very well go and draw the bending moment diagram, and this is already drawn for you over here. So this is the bending moment diagram over here. Now you see that in this diagram that you have over here, let's take a look at some of the points, right? So here you see here at A, which is the pin supported end, at B where you have that point of contraflexure, that your bending moment changes sign, so you have a 0 bending moment over here, and at D as a free end, you have the moment 0 over here. So at these 3 points, that is A, E and D, the value of your curvature must also be 0, right? So this is overall what you see is the deflected shape of the beam, and this can be, you can just visualize from this. We have not derived the equation of the deflected shape and so on, but this is just from intuition. If you have the beam with these loads, you would expect because of this load you have a sagging over here, and because of this load you will have a hogging moment kind of here. So the deflected shape of the beam looks something like that. Now what I was pointing to is that these 3 points that you have over here, as we discussed, the bending moments are 0, and correspondingly your curvatures must also be 0 over here, right? So that is one of the key takeaway points, that you have a 0 curvature at the points of 0 bending moment. Now let's go ahead and take one step further. Now you see this region over here from A to E, say at this particular point you have a positive bending moment. That means that your kappa must also be positive in this particular case. Why positive? Because you see in this region you have a sagging kind of a figure that you have over here. So if sagging means positive, correspondingly you have a positive bending moment, so your kappa must also be positive, right? So essentially this region or this region over here, your kappa is positive. So the beam is concave upwards, where the moment and the kappa is positive. It's a concave upward shape, so you have the moment, or the sagging shape, you have the kappa is positive over here. Now let's look at the other region. You see here in this beam from E to D, you have a negative bending moment and correspondingly a sagging kind of a shape over here. So that means your kappa is negative. So both M and kappa is negative. So it gives you overall a sense that how your beam deflects, what is the overall shape of the beam that is there. Now can you tell that in this beam where your kappa is going to be the absolute maximum, you're right, kappa is going to be absolute maximum where the bending moment is maximum, which is essentially at this particular point it will be a negative maximum of kappa that you have over here. So essentially at the point C you will have the kappa, which is a maximum. So maximum curvature happens where the absolute moment is maximum. So in this case it's negative, so your kappa maximum, absolute maximum, it happens over at this particular point C over here, right? So you see overall the point which I was stressing over and over is that the curvature helps you in some way to establish a sense of the beam, and you will see soon that essentially you are deriving your deflected shape of the beam. You are trying to find the deformation of the beams or the deflected shape of the beams, right? So that your curvature is going to play a key role in for you to find out the deflected shape of the beam that is there, right? So what we essentially need is an equation for the beam shape, and this equation is also very important. It is known as the elastic curve. Bottom part is not getting circled, but you get the idea. So you have the elastic curve, right? So the deflected shape of the beam, it is known as elastic curve, and what that essentially helps you. So once you get a formula, see here in this beam, your say y-axis points vertically up and your x-axis is about here. So as long as you get a relationship between your y and x, that will give you what is the deflection along the x, and along with the deflection it will give you the slopes. So what is the slope here, and slope here, and so on. So it will give you some sense of the slope over in this beam that is going to be over there. So with that being said, let's go ahead and try to take a look how to derive this equation of the elastic curve, and from that what are the techniques we can adopt to find the deflections and the slopes in the beams. To find the deflection of the beams, we are going to start with one of the very popular methods, which is known as the second order method for finding the deflection. So essentially remember, what we are trying to find is the relationship between the deflection y and the x-axis that is along the length of the beam that is there. So let's see that how do we start with the second order method and how that helps us in find the deflection of the beams. Now first I am going to throw at you several formulas which you hopefully have seen from your basic elementary calculus or differential calculus. So these formulas, and you should be familiar with this, and this is our premise where we start. These essentially gives you the relationship between your curvature, that is kappa, that is there, and this relationship that you see over here with respect to the double derivative of the deflection and the first derivative of the deflection that you have over here. So this relationship that you see, and the whole derivation of this one based on the elastic curve. Now remember, the deflected shape of the beam is known as the elastic curve that you have. Now this relationship, the derivation of this relationship is given over here, and we are not going to go much into the details of that. You should remember this from your elementary calculus, or if you have forgotten, you can take a look at this derivation. But essentially what you get at the end is something like this over here, which gives you an exact expression between the curvature and the deflection y that is there. Now remember that we are, in our case, we are predominantly looking at structures. For example, when we are looking at axial deformations or shear deformations or bending deformations, any kind of deformation, deflection is also a type of deformation which is happening across the entire length of the body. We are always looking at small deformations and small deflections that is this. Now if we take this expression, and this is reproduced over here, now if we take a look at this one over here, you see your theta, that is tan theta dy of dx. So for small angles, you have theta equals to dy dx over here. Now for very small angles of rotation, this dy dx guy is already very small, and here you're squaring that one over here, so that becomes very negligible that you see. So now if you make that assumption that for small angle of rotation, so if you're looking at small angles of rotation that you have over here, this guy goes for a toss, so your kappa essentially becomes equals to d square y by dx square. So now if you again tie the loose ends back together, what do we get? We had already seen that our expression for kappa equals to 1 over rho, which is over here, and also we had seen is equals to m of x divided by ei right? This is from the previous discussion that we had. Now this is also d square y by dx square, right? So now you take a look at this expression, and remember this expression is strictly valid for small deflections. If you're looking at large deflection problems, then you have to start with this elaborate equation that you see over here. For small deflection, this holds good. Now if you take a look at this relation, what we have just established is a relationship between the deflection y, the double derivative of this y, deflection of the y, and the moment over here. And since you start with a second order derivative of the deflection, and then how do we get the deflection from here? We have to integrate it twice. So that's why this particular method is known as the second order method. So let's write about this relationship, that it gives us a relationship between the deflection y and the bending moment m. Now that we have this particular relationship that is there, let's go ahead, and as we said that we are going to take this relationship that is there, that ei d square y by dx square, where what I have essentially done, I have essentially pulled this ei and taken over to the right side and did a little bit of rearrangement. So what I get is this important relationship that is there, which you are going to use quite extensively to find the deflection of the beams. And as I said, since we start with the second order derivative of the deflection, this method is also known as the second order method for finding the deflection of the beam. Now if you start with this guy over here, and then if you integrate it once and if you integrate it twice, let's see what we get over here. So if we just for integrate it once, what we will get is integration. Now here c1 is the constant of integration, and also you must remember one thing, that here we are assuming that your beam is prismatic, that your eye doesn't change, right? So this assumes that the beam is prismatic. If the beam is not prismatic, then in that particular case your I also has to be here, and this integral has to be m of x divided by I of x. Also remember one thing, that this dy of dx that you see over here for small angles, so we have the tan theta equals to dy over dx, or in other words, where tan theta for small angles becomes equals to theta. So for small angles we can write that this expression, that dy of dx, is nothing but equals to the theta. So that gives you, this theta is nothing but the slope of the beam. So that gives you an expression for the slope. So let's make a point of that as well. So once we have this, which gives us an expression for the slope, if we integrate it one more time, remember theta is nothing but dy of dx. So if we integrate it one more time, we are going to get the expression for y, which is the deflection. So let's do that. So this one gives you the deflection. Now you see in this equation, you have two constants of integration. So C1 and C2 are the constants of integration. And how do we get the C1 and C2? Simple, you get it from the boundary condition. So for a beam given a set of loading, you have to sort of go ahead and figure out that if you are doing the second order method, that what are the boundary conditions which I am going to use to determine this constant C1 and C2. So C1 and C2 are determined from the boundary condition. So we have determined C1 and C2 from the boundary conditions, and what can be some of the boundary conditions that you can think of. For example, for say if you're looking at simple statically determinate beam, so we'll start with some very simple examples. So you see here in this beam, for getting the two constants of integration, so a couple of boundary conditions for you can be that at x equals to 0, so for this beam you see it's an overhang beam with a tip load at the end. At x equals to 0 you have y equals to 0. At x equals to this length, that is at b, you have y equals to 0. If you have a beam with a UDL at the left end, at the right end also your deflections y equals to 0. Now for the cantilevers, this is a case where you have to make use of the y as well as the theta. We have an expression for the theta which depends only on your C1, right? And for this case, you see at the cantilever end you have the deflection and as 0 as well as the slope as 0 as well. So these are some of the simple examples, but if you take a look at slightly more complicated examples with a variety of different kinds of loadings, so in that case you have to have some expressions for the continuity of the displacement and the slope. So let's go ahead and take a look at some of these examples to use the second order method to find the deflection of the beam and the slope of the beam. And let's see that how we use this method also for certain cases where you have an intermediate loading which requires you to establish further relationships of continuity between the displacements and the slope. So let's go ahead and do a couple of problems. So the first example problem which we're going to look at, as you can see, is a simple cantilever beam with a tip load at the very end. And what you are asked to find the deflection at A and as well as the slope at A. Now we know that in this beam here the deflection will be highest, and you can expect the value of the deflection you will get as a negative value, because here say if you take this your positive y and your positive x, your beam goes vertically downward. So let's go ahead and try to do this particular problem. I purposefully put the figure over here so that even if I scroll down you will get to see the original figure and have a sense of what is going on. So if you take a look at this beam, and let's quickly draw for our convenience the cantilever over here. Remember that what we have already at our disposal is this relationship. So we essentially have to find the moment at how it varies along the length of the beam. So now here let's go ahead and mark the axis that we already just talked about. So I have my positive y axis over here and the positive x axis over here, right? So let's go ahead and from this particular origin, let's write the expression for the moment at the different points along the length of the beam, which is very simple. It's going to have one standard expression here for this case. So to get the expression for the moment, for example, is using the method of section. So if we go ahead and draw a section, say at any distance x from here, and if you write the equilibrium of that particular section, what you have is something like this. So you have the beam where you have, this is your load P. Now at the right hand side of the section, I'm going to mark my positive shear and my positive bending moment that is there. Remember, the positive shear is the one which tries to rotate your beam in a clockwise manner. So this is my positive shear V, and the positive bending moment is the one which causes your beam to sag or your beam to smile. So this is my positive M and M over here. Now here I'm mostly concerned with this moment that is there, and I know that this distance is X. So from this one you will get the expression that M of x equals to minus p times x, that is there. So now I am going to go ahead and take this and plug this back over here, do the double integration. First find the expression for the slope, then find the expression for the deflection y, that is there. So let me go ahead and do that. So you see in this one, I have integrated this once over here and I get this expression. So integration of minus px dx is minus px squared by 2 plus the constant of integration c1. You integrate it again, you get this guy over here. So now as you can see, we have to find our constants of integration c1 and C2 over here. Now how do we find that? Using the boundary conditions. Now here the boundary conditions can be what? So at this end B that you have over here, so that is at x equals to L, your slope is 0 because for the cantilever where the part that is fixed, you have the slope is 0, as well as the deflection y equals to 0. So we can use those two boundary conditions to find the constant C1 and C2. So let's go ahead and do that. These are the two boundary conditions at B, that is at the point B, that is at x equals to L. You have the rotation as 0, the slope as 0 over here, and you have the y of B that is equals to the deflection of the B equals to 0. So if you plug those two guys back over here, for example, if I plug the boundary condition 1, this one, into the first expression, you will get the value of the C. And after you get the value of the C, you put it back over here and you put this condition back in this expression, you will get the value of C2. So once you do that, the values of C1 and C2 that you will get, I'm not writing all the entire steps and details because this is very preliminary algebraic manipulations that you have to do. So what you will get after substituting in the equations, so these are the constants C1 and C2 that you get. So and once you have the constants, you can plug back in over here to write the expression for the slope and the expression for the deflection. So let's go ahead and do that. So once you have written out the expression for the slope and the deflection, see, the problem asks you to find the deflection and at the slope at A. So that means at A, we know that x equals to 0. So if we go to A over here, so here this particular point is x equals to 0. So if you put the value of x equals to 0 over here, you will get the value of the slope, that is theta at A, that is dy dx at A, and also the y at A. So let's go ahead and plug x equals to 0 and let's see the expressions that we get. So these are the two expressions that we get: PL square by 2 EI, that is the slope at A, and minus PL cube by 3I. And as we said in the beginning, we expect a negative sign because we know it's the negative deflection. So the slope is positive. So let's go ahead and draw the deflected shape. Even if you don't have this from plain intuition, you can draw the deflected shape. So let's go ahead and draw the deflected shape and mark the points. So this is the deflection, and you will see that over time, as you keep on writing this equation, it becomes sort of ingrained in your memory that if you have a cantilever with a tip load, the deflection works out to be PL cube by 3 EI, and the slope is PL square by 2I. So slope is a positive slope and the deflection is negative because it goes vertically downwards over here. Now, one thing you would also want to check is that when you have these deflections that is there, that you can plug back the units of E, I, L cube. So you will see that this expression goes to the order of mm or inches or so on. And if you should also plug back into the expression of this one, to find the units of the slope of the rotation that you get over here, right? So I hope this problem example was clear. So in this one, we looked at a cantilever beam with a load at the tip. Let's go ahead and look at the second example. So the second example problem is a beam with a overhang, a simply supported beam with an overhang with a load P at the very end, and the dimensions are given overall. The first part of the problem, it asks you that for this overhanging beam to find the equation for the elastic curve. So it asks you to find the equation, so not in terms of the numbers but just how y is a function of x. Also the what is the maximum deflection, and remember all of this and the last part it asks to evaluate after you plug in the numbers. Now all of this it asks for just this portion AB, and there is a reason why, and you will later understand why it asks only for AB and not at the point C over here. So let's go and start and doing this particular problem. So in this problem as well, if we go ahead and take a section somewhere over here, say at a distance x from the left end, and if you write the expression for the moments over there, now to write the expressions for the moment you would need to find the reactions first. So this is already solved. I will write the reactions over here. You can go back and check it later. So these are the reactions that you get. So at the left end is minus P over L. So essentially it pulls the beam downwards over here, right? So now at a distance x, let's draw the free body diagram and write the expression for the moment. So this is the free body diagram of the beam. So I'm going to write the expression for the moment now. So now that I have an expression for the moment, I know my basic relationship, that is EI d square y by dx square equals to m of x. So I'm going to plug in that one over here, integrate it twice, first to find the expression for the slope and then the expression for the deflection. That will give me the equation for the elastic curve. So these are the two expressions that I got, first for the slope and then for the deflection. Now my boundary conditions are that, now remember this expression for the moment is valid from x equals to 0 to x equals to L. So here maybe I go ahead and draw my axis. So this is my positive y and this is my positive x, and this expression is valid from x in 0 to L, that is over here. So now what are my boundary conditions? So I have two unknowns, that two constants of integration. The boundary conditions are that since it is point this is pinned over here and it's a roller over here, so the deflection at x equals to a or at x equals to 0 is 0, and at x equals to L also y equals to 0. So let's go ahead and write the boundary conditions. Now once you use these two boundary conditions over here and you plug in both of this, so for and in this one this equation doesn't yield anything. So for since you are dealing with the deflection y, you plug both this back in over here and you get the following values for the constants of integration C1 and C2. So now that we have the values of the constants of integration, I'm going to plug this back over here to find the equation for my elastic curve. So the first part asks you to derive the equation for the elastic curve. So that solves the first part, and then it says find the maximum deflection. So how do I find the maximum deflection? It is simple. Now that we have the expression for the deflection, and remember this is only for the place for the region AB. So this is valid only for the region AB, that is from x equals to 0 to L. So I'm going to differentiate it once and equate to 0. So that will give me the location x at where I in the beam where I can expect my deflection y in the region AB to be the maximum. So let's go ahead and take the derivative and equate it to 0, and let's see what is the point where in the region AB I have the maximum amount of deflection. So you get that at x equals to L over root 3, you are getting the maximum deflection. So if we go and plug this guy back in over here and plug in the other estimates that I have, that is L equals to 4.5 meter, E equals to 200 GPa, you are also given the second moment of the area, that is 300 raised to 6 mm raised to 4, and also the value of A that you see, which is given as 1.2, you will get the following number. So you see, this you get the value of the y max in the region AB, and it comes out as positive. So that means the deflection is in the upwards, and it's also obvious if you just go by simple intuition. If you are pushing it over here, the deflected shape of the beam would look something like this. And at x equals to L by root 3, which may be somewhere over here in this region, you are getting this maximum deflection. So I hope this problem example was clear. So at x equals to, so maybe let me mark the distance. Right, so I hope this problem example was clear how we got this one. Now remember that, as I said, that this is valid, whatever we did is only for the portion AB. Now if you were dealing with BC, you see the expression for the moment would change. So then you have to go ahead and solve this for a different set of numbers, different sets of equations, and there is a problem later which tells you that how, because essentially you have a region of discontinuity, you have a point load over here, a region of discontinuity over here. So all these things are easy to do when you have no discontinuity, you have only one expression for the moment dependent on x from the left hand side over here. Now that this problem example is solved, now what I want you to do is you can go ahead and try solving this problem example, where maybe you have a simply supported beam with uniformly distributed, and say a length L. You will see for this one, if you go ahead and solve it, again just calculate the reactions here, start from the left end, you will see the deflection, and it's obvious here the deflection happens maximum at the center, and the value of the deflection, this is also a very standard problem which if you do several times it gets just ingrained in your memory, and for this case you will get the value of the maximum deflection as y max is 5 by 384. It will be negative because it happens down, WL raised to 4 divided by EI. So go ahead and try solving this problem and see that for this example if you get this expression or not. This is a problem example which has a discontinuity in the beam within itself, that at this point P, and you have an applied load, and it asks you to find the slope and deflection at D, at exactly at that point. Now here you cannot do away with just writing one expression for the moment over here, because you are asked to find the slope of deflection exactly at the point of discontinuity over here. So here you have essentially two regions. region 1 from 0 to L over 4, and region 2 which is greater than L over 4 over here, that where you have to find out the expressions for the moments, and then as a consequence of that you will get 4 constants of integration, because they're dealing with 2 regions of the moments. We'll write the expression and you will see soon. So now the question is that how do we solve these kinds of problems where we have a discontinuity of the nature which you have in this expression over here. So let's first go ahead and write the reactions for this one. So the reactions are pretty simple. For this beam you have this Ra. These are the reactions, and let's just mark our regions R1 and R2 over here. And so for R1, so R1 is the region between 0 to L over 4, and R2 is the region between L over 2 to L, that is the end of the beam that you see. And let's say like the expression for the slope in this region is by theta 1 and the y is y1, and for R2 it's theta 2 and y2. So let's go ahead and write that. And also at certain distances x, so if I take in the first region, if I take say a section over here, or in region to a section over here, since we have to have 2 expressions for the moments to solve this problem, let's go ahead and write the expression for the moments as well from the free body diagram. So I just go ahead and draw. You can follow, or you can write your own expressions and then come back and check whether you got the right answers or not. So we get these overall expressions, as you can see, for the region 1 and the region 2. Remember, this theta 1 is dy dx for region 1, and y1 is the y for the region 1, and similarly here, right? So if you take a look at these equations that we got, so let's just mark them, maybe 1, 2, 3 and 4. You see over here we have 4 constants of integration that we need to evaluate. So we need to evaluate C1, C2 and C3 and C4. So we need 4 boundary conditions. But now if you take a look at the overall beam, what are the boundary conditions that we have? The boundary conditions that we have are that at x equals to 0 you have y equals to 0, at x equals to L also you have y equals to 0. So that helps you get 2 equations. So what is the other 2 equations which we can use? Maybe you have guessed it right. The other expressions we can use here at exactly at this particular point, at exactly L equals to 4, right? If you are coming from the region 1 over here, the theta 1 that you will get at x equals to L over 4 must be equals to the theta 1 if you're dealing with region 2. So the slope, so that is the continuity of the slope. And also similarly, even if you're coming from region 1 or region 2, the value of the deflection must be the same. So the deflection is just one unique point that you have, that cannot be different from if you're coming from the left or dealing with the region 1, or if for the right if you're dealing with the region 2. So we have the expressions for the displacement continuity as the slope continuity as well. So let's just go ahead and write down the boundary conditions that we have in this problem. So out of these expressions, these ones are the easy ones from the overall beam and the support conditions that we have. So this one is a slope compatibility and this is the displacement compatibility. So now that we have these ones over here, all these expressions, so you had 4 unknowns, C1, C2, C3, C4, 4 conditions. If you go and do the algebraic thing, and then you will evaluate all the constants of integration that is there. So I'm going to go ahead and write that. You can calculate and check. So now that we have the 4 constants of integration, you can go ahead and plug in and you can essentially find the deflection and the slope anywhere, right? So this problem asks you to find the slope and the deflection at the point D. So if you substitute at x equals to L over 4 in any of the expressions that you have over here, what you will essentially get are these values. So these are the values for the theta d and the yd, that is the slope and the deflection, the d that you have over here. And if you kind of try to draw the deflected shape, it would look something like this. Now one thing to note, you see that this theta d, it has a finite value, which is the value of the slope over at this particular point d, that is there at this point, that is the slope. It's a negative slope, as you can see, right? And also the yd is negative, that means this point d is actually going down. Now you see that is it possible for us to tell that whether the point of d is the maximum deflection? It's not. If it was the maximum deflection, then the slope at that particular point must be equals to 0. So here the slope is not equals to 0, so theta d is not the point of maximum deflection, right? So I hope this problem overall was clear to you. So we dealt with 2 different regions within the beam, and now also you are probably starting to get a sense, a hint, that if you have multiple loads, you have multiple points of discontinuities, you will have multiple expressions for the moments and as many, or actually twice the number of constants of integration to solve problems using this particular strategy that is there, right? Now in this one we use the 2 different regions. So we use the end conditions as 2 of the boundary conditions over here, as well as we use the slope compatibility as well as the displacement compatibility. Now, in addition to the second order method to solve beam deflection problems, there also exists a fourth order method, which eventually you will see it reduces to the second order method itself. Now, this fourth order method that you see, that is particularly useful when you are solving for beams which has a uniformly distributed load. And the reason why it is useful is that we will see in a minute that if you take the fourth order derivative of your deflection, that becomes equals to the load. And let's see that how does that happen. But as I said, that the fourth order method, once you start to integrate that, if you integrate it twice, you end up with d square y by dx square, which eventually boils down to the second order method. So if you have, say, beams, for example, here with a uniformly distributed load and so on, and we know that with this relationships we had studied from when we were looking at the chapter on shear force diagrams and bending moment diagrams, that our dm dx is equal to your shear, the derivative of the moment is equals to the shear, and the double derivative of the moment equals to dv dx equals to minus w of x. Remember, w is acting vertically down over here, that's why you get the negative sign. So this relationship, as you see, and let me maybe mark that explicitly over here, that where we have studied this from. So this we have studied from our SFD BMD chapter, right? So if you go from this one over here, now you know that one relationship that we have, that our EI with d square y by dx square equals to m, which we have seen already in the second order method. So what did we see in the second order method? That if you recall, that our EI d square y dx square equals to m. Now if you take the double derivative of that one again, you end up with EI d4y by dx4, which becomes equals to, you would have to take the double derivative of this one, which is this guy over here, and from these two the first 2 bullet points that you see, these 2 guys, you can write this one as simply equals to this one over here, and which you see over here equals to minus w times x. So essentially now you have a relationship between the fourth order derivative of the deflection and the distributed load that is over here. So it all follows from this interrelationships between the moment and the shear and the load. So now from here, How do we get the value of W? You're right, you have to integrate this 4 times. So now since you're integrating it 4 times, you will have 4 constants of integration to deal with. So if you integrate 4 times, you essentially get something like this, and you get 4 constants of integration: C1, C2, C3 and C4. And how do we determine these constants, these 4 constants of integration? Again, from the boundary conditions we look at, right? So we look at a short example problem, and as I said, you will see that in that one, the 4th order method, when you integrate it 2 times, you end up with the 2nd order method. So you can just start the problem with the 2nd order method itself if you want to do it, but just for the sake of demonstration, let's do a problem where we start with the 4th order method and boil down to the 2nd order method and eventually find the deflection of the beam. In this example problem that you see, you have a beam with a uniformly distributed load W, a beam of length L, which is supported by a pin support and a roller support at the other. In one of the problems before, I had asked you to try solving this beam using the 2nd order method, and I hope you have got the answer that we looked at. Now if we try to solve this using the 4th order method that we have over here, we can write the basic equation to start with as EI. Now in this case, since W is a constant, I can simply write it as equals to W over here. Now if you integrate it 2 times, you will get d square by dx square, and you will introduce 2 constants of integration. So let me just go ahead and write that. Now remember, here we have now introduced 2 constants of integration, C1 and C2, and if you recall that EI d square y by dx square is nothing but equals to the moment m. So this guy is nothing but equals to m of x. So before integrating it 2 times again to get the y, we can solve for C1 and C2 here directly. And how can we do that? See, this is a simply supported beam over here, where we know at the left end, that is at x equals to 0, I have the moment as equals to 0 because it's a pin support, and at x equals to L also the moment equals to 0 because it's a roller support over here. So if you substitute those things over here, that is at x equals to 0, this entire quantity is 0 because the moment is 0 over here, and also at x equals to L, this entire quantity is 0 because moment equals to 0. So that will give you C1 and C2. So let's go ahead and do that. So now that we have evaluated these 2 constants, C1 and C2, we can go back and plug that in this equation over here. So now we'll have EI d square y by dx square equals to minus Wx square by 2 plus WLx by 2 plus 0. So let's go ahead and write that. So had you started this problem using the 2nd order method itself, as I had asked you to do, then you will begin your problem with this equation. This, remember, is nothing but at any section x, if you take the moment, that comes out as something like this over here. The rest of the problem is more or less the same, that you integrate it 2 times again. So you get 2 more constants, say C3 and C4. Then you use the other 2 boundary conditions, that at x equals to 0, y equals to 0, at x equals to L also y equals to 0. So let's go ahead and plug those things, and let's see what we get as a C3 and C4. So you will get your C3 as minus WL cube by 24, and you will get C4 as 0. So if you plug this guy back over here, then in that case you will get your the equation of the elastic curve. So let's go ahead and plug that and get the equation for elastic curve. Now from this equation, see, the problem asks you the equation of the elastic curve, which we have gotten here already, and the maximum deflection. Now you can do dy dx equals to 0 and find the location. It is very obvious here that the maximum deflection is going to happen at L over 2, and the magnitude of the maximum deflection is going to be So this is the estimate of the maximum deflection that you get. So you saw, I hope you understood this problem, that how we from the fourth order method we integrated it twice and you got the second order method, and after that the rest follows how we did before, that you integrate it twice again, and in all the steps you determine the constants of integration using your boundary condition.